Kind of going, the idea sort of behind this is to sort of look a little bit from a different side. Instead of actually writing code, we're actually going to look at just sort of see how the actual what's produced from the code, and get a little bit of an understanding of actually why certain things are sort of constructed the way it is. So who am I? So my name is Joakim Kennedy. I work for Anomaly, which is one of the sponsors here. My role is as a threat intelligence manager. So we have a research team that's based here in Belfast. What we do is we research sort of threat intelligence stuff in terms of sort of strategic views that Kalen presented on earlier. But we also do technical stuff where we might sort of analyze malware. We might build tools to collect data and process a lot of stuff. So sort of a big area that we cover. So for the agenda for this presentation, I wanted to sort of, there's a lot of stuff going on sort of under the hood of the binary that's produced by Go. So what we sort of going to start out with is to just glance over a couple of primitives that the language is using and how they are defining it differently to other languages, mainly because we will see them in examples. And then just going to look at just a hello world, see what the actual produced sort of assembly from that, and we'll compare that to some other languages. And then sort of the main focus is to look into the type system. So Go is sort of statically typed. It's very strict, and the idea is to just look at how is that actually implemented, and sort of stepping back from that. Once we have all this information, what are some other use cases we can do that? Well, if we know how we can get this information, what can we use it for? So just to start with, so obviously Go has sort of a support for the most common types. So if you think about any integer types from 8 bits to up to 64-bit, we have complex and stuff like that. But on top of that, it does have directly support for strings. The way it's implemented is by a 2-word sort of struct. It's sort of a difference to C that would actually just use a null terminator. And the first pointer is to where the data starts. And the second is the length. So obviously a benefit in this is we have a constant time lookup for the string length. The other thing that they have is a sort of a support for an array type. This one is less sort of common, less used in the language, mainly because the size of the array needs to be known by the at compile time. So instead, sort of on top of that, the language actually has sort of slices. They're more similar to Python's lists in sort of the implementation. So it is an abstraction on top of arrays. And what they have is a 3-word struct. First one points to the data where it's located, sort of is a classic array. The second one is actually the length of that, so how many entries. And the third one is what's called a capacity. If the capacity is 0, the struct or the slice can essentially grow infinite in size. So there's no cap. But if you have a value, then it can't go sort of larger than what sort of the length is set. So this is actually what simplest sort of the Go program you can write. So there's a sort of hello world. The way sort of the language is set up, everything belongs to a package. So you have, here's the main package. It's just importing a format package to do the printf or the println here, which will just print with a new line. And if you compile that, I hope that's, that didn't turn out great for you guys, I'm sorry. So this is actually the whole function that's actually returned. The difference with sort of code that you would compile in C is that Go by default is actually using statically compiled as a sort of an output. So everything gets put into the binary, including all the third-party libraries and standard library. So actually what you have, so this is a very, very typical Go function. The first thing you have up here is a check for the stack size. Why it's doing that is because Go implements something called like a tiny stack, and it is to support the large concurrency. So you can spin up a lot of different sort of concurrent functions, and each of those will have a very, very small stack. And then the functions will check the stack, and if it needs more, it will request more, and it will grow. It is sort of like a performance way of doing it. But it's very, so you see this kind of stuff. The other thing, what's happened here is that the compiler actually directly lying to us. It has inlined this whole println function. So what we're actually seeing is the this area here, that's where the string is located, and beyond that is actually the inline function. If you compare that to C, so here on the top we actually have just a classic hello world, and it's using printf, compiled for 32-bit, and then below it is the 64-bit. Quite interesting that it turned out a little bit different, but it's GCC obviously has slightly different optimizations for the two architectures. And first thing you kind of see directly when you're looking compare these two languages, there's no pops and push in Go. They opt for using moves. Would anyone here have somewhat of an idea why they're opting for that? So faster. It's faster, yes. And obviously C has been optimized for size. So this column here is the size of the instruction, and here you can see that C code is much, much smaller. Actually, we'll stay on here. So with regards to the calling convention for Go, everything is actually pushed on the stack, or everything is actually moved on the stack, to be correctly. From here on, you can see it will actually move a couple of, so here, it starts from here, ECX will be moved, ECX will be moved onto the ESP, and then everything is just moved on top of that. So it moves it on. The function returns is quite interesting too. So Go supports the return of, I don't know what the maximum is, but multiple return values. So it's not limited to one like most languages. And this is just an example that's being used. This pragma is just to tell the compiler to not inline it, which that will do otherwise. And if you put that out, so here's the call to getting sort of an argument off to call in this function. And it will pull the return values off directly from the stack. So function returns and function arguments are all pushed on the put on the stack and pulled back the same way. So it's kind of a little bit how it's compared different to assembly generated by C. Actually, with regards to that, are everybody familiar with how C is actually doing the calling convention? Okay. C would actually 64-bit using a version of sort of a fast call where it would put the first few arguments in a couple of registers and rest on the stack, and then return values always return in EAX or RAX, which is a general purpose register. 32-bit on Unix will use the stack to push the arguments in sort of like inverted order, and then return it on EAX. Where so here we have Go returning it everything on the stack. So let's look at sort of the types and beyond sort of that. So for this, we're actually going to use an example. This is similar to what a type def in C. So we're actually defining our own type of a struct. Let's just call it a simple struct. It will have two fields, a string and just an integer. then when this actually function, or when the main is actually called, so right after we see the call to increase the stack, we see this call to a new object. And we have we have actually a predefined sort of global value sitting here that actually is passed into this new object function. When you dig into what this function does, it will pull out a value and then call essentially malloc to allocate the memory. And then after that, it will start populating. So we can see it takes that value off, which is similar to what, it will be a pointer to where this allocated memory is. And it starts populating, and we can see how it's putting at the second field the hex value of B, which is the length of the string. So it's starting to populate the string here. So when you look into what this function is doing in the standard library, it takes actually, so here's actually what the structs look like. And this function actually takes a type called an R type or an underscore type. This structure is defined in two places in the standard library. You can find it in the reflect package, which is used for reflection, or you can find it in the runtime. And this is how Go tracks what is what. So we can essentially parse this data struct that we have in there. Sort of just reading it. This is for a 32-bit, so we don't have to deal with sizes that are dependent on the architecture. So and nothing's going to be 64-bit in size, which is kind of nice. But just going from the start, we'll actually have this is a pointer to the size. So we have a value of, so this is what actually malloc would allocate for this. This is the number of bytes that could be pointers. If I'm not incorrect, I think it's used for the garbage collector. So it knows if there might be some pointers in this data struct. Obviously some hashes, and these are some flags. The most interesting one there is the last one called the kind, which here in the document, in the comment says it's an enumeration or an enum for C. This actually tells you what it is. So if you look up in the source code, the enum, you can find that this value is actually referring to a struct type. Some stuff that's used for the garbage collector and for comparison of other types. And then we have two other pointers or offsets. These are quite interesting for reverse engineering because they actually will contain the actual string representation from the source code of this. Not the source code, but actually the name of it. So I know what this struct is called if I can sort of find that. So we have the first, but there's more data sort of sitting under this area. By using sort of the kind, and when sort of digging through the source code, find out that it is what's called a struct type, and there is actually there is a type in the runtime and the reflect package of this type, and it looks like this. So actually, what we weren't looking at was not an R type. We're actually looking at this struct type, and the first sort of field there is this type that we looked at, and then we have the package name, which in this case would be main, and then after that we have what looks like an array or a slice. So this would say that it is two struct fields, and interestingly, it points to right after it. There's something in between there. And looking at this in the source code, this is the data structure that is right below it. And we have the same way, we just have the name, which will point to a packed sort of byte array that will contain some information about the name. The type for that struct, and then it's offset in the field or in the struct field, and it's just repeated the same over again. So what about this in the between? if you're looking at the flag, so there was one of these bytes, there was a flag. It has what's called a unknown or an uncommon, and this is the documentation. It tells you there will be another sort of type appended to it right after it. It looks like this, essentially, for the struct type. And interestingly here, we actually find some reference to methods. So from here, there will be an offset to where the instruction of its, or description of its methods, actually not directly the method, but a way for you to find it. So summarizing this whole data struct, it looks like this. A lot packed into 60 hex. But essentially we have this initial type, we have struct field coming in sort of after it. So let's jump a little bit over to sort of methods. So this is how you sort of attach a function or a method to a type. It's a little bit more, it is technically some candy around it. The compiler sort of treats it essentially as a function, but will pass the type that it belongs to as the first argument. But that's all happening sort of behind the curtains. It can be done on any type. It doesn't have to be sort of structs or anything. It can even be a function, because a function in Go is a type. So you can have function that has methods. That's even there's a comment on it in the standard library, where you wonder why a function would have methods, but it seems interesting. So this uncommon struct, it points to an offset to where it says you will have an array of this type. It's pretty straightforward to parse. These are what looks like weird types. What they are is just predefined. They are offsets from sections where this information will be stored. It includes the name. The interesting part is the M type, which is function signature through sort of the type system, and then points to where it will be located in the text section where the actual code is located. So if you walk one of these arrays, so here's an example of a decimal, which is a type for convert strings to decimal values in the standard library, I'm pretty sure. I wrote a parser for it, I ran through it, and it found 9 methods. If you look up, it is correct. There was, in the version I used, it had 9 functions. Not all of them exported. It lists all these methods. If the name starts with a capital letter, it's exported. If it's not, it's a private. But interestingly, I can still find it, get the name of it. What was quite interesting was some of these functions have nil values, so it tells you there's nothing there. Source code says it would be, but it wasn't. So that's when you start, and looking at the symbols of the binary, they were not there either. So that's when you start wondering, and you go sort of to, I guess, the book of knowledge, Stack Overflow, and you find, oh, apparently they started to prune some methods and stuff like that. So there's a support for method pruning. So it can bite you if you're not consider that, because it's not documented in the source code. So methods and sort of comes then into looking at sort of the interface. So the way a interface is sort of defined in Go is through using a method signature, which would be the function signature, and then the name. This is from the specification. It's kind of dry to read, but that's essentially what it means. So the way you would actually implement a interface in Go is you actually have, this is the interface for what calls a stringer. All it says is, has a function called string, and it will write the string representation like in most languages. And all you have to do is basically create a function with the same name and the same signature, and that's it. So they definitely sort of adhere to the duck typing, where if it walks and quacks, it's probably a duck, which is essentially what they do with, if it looks like an interface, talks like it, yeah, it's probably the interface. So there are those two things that is important for a function to sort of satisfy an interface. So if you, how does the compiler then, or how does actually the runtime or the compiler sort of check if it actually is implementing the correct interface? So there's those two things. So this is actually a function from the reflect package. So reflection is to figure out what is by dynamically determine what kind of type it is at the runtime. And you can pass in two arguments, an interface or a second interface, or that last one can actually also be a concrete type. And what it will do is to cast them to these, it is pointed to these R types. It will cast them to there's a type called interface type. Trying to be careful with the language because there's a lot of types in the words. And from there, it will pull out all its methods. And it will iterate through it, get the file, get the name, and get its signature. And it does, and then it takes the other one and casts it to its own sort of type, which is the common type. Get the methods out and pull it out. So you have just a linear search where you see here essentially the comparison. If all these pass, then it will just return as yes, this is implemented. So it's nothing more complex than that. So there's some caveats though when it comes down to sort of analyzing Go binaries. So I sort of want to share some of the pitfalls that I've fallen into. So when you're assigning a method to a specific type, you can decide to do it on the pointer version of it or the actual concrete version. The pointer allows you then, there's a little bit of an optimization saving because instead of passing the whole data structure around in calling functions, you'll just pass the pointer. What happens though in the sort of under the hood is that all those methods will actually be attached to a type of the pointer to that type, which is it's not a void type, it is a specific type for the pointer. It's a specific pointer type to that structure or whatever it is. It's very strict in terms of how it's not every type, so not every pointer is the same essentially. They define what they're pointing at. So here's, for example, if you write it in, where you define it to this type, it will be on that pointer versus actually the concrete version. As you saw from the Stack Overflow, versions prior to 1.6 are fine, but afterwards you have to be considered with sort of nil pointers. So kind of have to add some extra checks. The other thing is all these structures have changed throughout time. So if you're writing something that needs to analyze from binaries compiled now and back 3 or 4 years, there's a lot that needs to be covered because they've changed. Luckily, everything from 1.7 beta 2 and now is basically consistent. Interestingly, that version has the method struct, instead of having sort of int 16s, it has 32s. So if you miss that one, you throw your parsing off completely and you start just trawling down something else. 1.6, which is the one so last 1.6 and prior have a very, very, very different structure. So you kind of have to implement it completely differently. But I think we're talking about 3-4 years back now, since those compiler was released. The other thing, just 1.5 and below has an extra type in that R type that points to what its nil value would be. So when you put all this stuff in together, what can you sort of use for it? So the whole idea behind this was to be able to analyze unknown binaries. All this information can be used on stripped binaries. This is information that consist constantly. So it's like they're not tied to debug information or symbols. Here's an example where I analyze a APT malware. So this is actually a Russian threat group. This is a backdoor that's been deployed quite heavily lately. It's quite simple in terms. It just collects some information, sends it back to figure out if it needs to pull down new other malware, and they will go further. So it's more of like is this the right target that we're after? Here's another example where we use sort of this information to pull out the data structs, and this is one of the first Go malware that was actually reported by Dr. Web. I think it was the first one. So this one is from 2016, I think. But knowing this information, we know what sort of the payload and stuff like that. It gives us a good understanding without even looking more at the binary, or we can get a good understanding of what it might do without actually going deep into it. So, summary-wise, compiled code from Go has kind of a distinct look. It's tracked heavily, sort of the type system. It prevents it from being cast to stuff it can't be. The very interesting thing from sort of an analyst's perspective is that even if information is sort of marked as private, you can pull it out and sort of reconstruct an idea of what maybe the source stream would have looked like and things like that. So kind of good information in regards to be careful. It will include sort of like your file system paths. So if you're doing something malicious, don't compile it in your home directory. Thanks, guys.